Okay, so I'm going to talk here about quizzes 13. No, I just talked about that. Quizzes 14, 15, and 16. So in these quizzes, they dealt with sorting and searching. So I just took this sorting and searching code that we developed and put it in another little function here called quizzes. And I put in this array that was given on the quiz. These are the unique digits of pi, 314599268, and just made a copy of those into this B array. So A and B both have these values. So I'm printing out quizzes 14 and 15. Well, quiz 14 asks us to describe insertion sort and then use that to sort this and kind of show each pass of that. And then the same with selection sort. So I thought we would take a moment and kind of recap what those sorting techniques are actually doing. Let's start with insertion sort. And you can see where I put in some extra code here as well. We actually did some debugging code like this in class. But basically insertion sort takes an array, and what we want to do is look at this outermost loop. So note that there's an outermost loop, that's the I variable, and an innermost loop, that's the J variable. Now, what we're trying to do here in this innermost loop is identify where in that list of size, well, this number plus 1 up to this index, where the item at that index belongs. So what I need to do is start at that index and work my way down. Essentially, I'm just taking the ith entry and inserting it somewhere between 0 and I in the position where it needs to go. So we're starting kind of at the high end of that, I minus 1, and just seeing if we can place that in there wherever it needs to go. And then we're shuffling these items up 1 point or 1 position if this condition is true. Once that condition fails, we've found a place to insert the item, and then we can place the item there and then go on to the next item that I need to place. So we're successively going item by item, inserting it in the previous items. So the previous items are always going to be sorted, and we're going to go from there. So let's look at that right down here. So here's insertion sort in action. So note that I have these elements 3, 1, 4, 5, 9, 2, 6, 8. So if I have a list of size 1, it's sorted. That's just my 3. Now I want to insert, so that's what I'm printing out here. Now I want to take this next item 1 and insert it somewhere in here. Well, 1 is less than 3, so that's where it goes. Now so I've placed the 1 where it needs to go. Now the 4, I need to place it where it needs to go. Well, look, it's already where it needs to go. And then moving down here, 5, that's the item I want to insert in this list. Well, it's already where it needs to go. So moving down, I want to go to 9 and insert it where it needs to go. Well, it's already there. Now at this point, I'm inserting 2 where it needs to go. So 2 is less than 9, it's less than 5, less than 4, the less than 3. But it's not less than 1, so it needs to go at this particular position. And then finally, I'm going to insert, well, no, not finally, but I guess I'm going to insert the 6 next. So 6 is less than 9, so it goes like there. And then finally, 8 is less than 9. So at the end, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So each successive pass of this outermost loop is taking the ith entry and inserting it somewhere in one of the first I positions, wherever that needs to go. So note that if I draw a diagonal down here, everything to the left of that diagonal is going to be sorted, whereas everything up above it may not be sorted. It's possible that if I start with a sorted list, that everything is going to be sorted, but in this case, we're just guaranteed, well, we're always guaranteed that below the diagonal, these elements are going to be sorted. So that's quiz 14. Now let's look at quiz 15. Quiz 15 dealt with selection sort. And so selection sort works it's kind of similar in some sense, that we have a pass. So, but at every pass, what we're going to do is look for the minimum element of the items that haven't been sorted yet and place that at the beginning of that unsorted list. So right now, nothing is sorted. So I want to start. So note that the number of passes I have here is one less than the length of the array. Note that in insertion sort, we also had one less than the length of the array. Here we're stopping before we get to that last element, and in insertion sort, we're starting at the first element. All right, so what do we need to do? Here, when I start at index 0, I want to start here and find from 0 all the way to the end, what is the minimum element? That's what this code is doing right here. It's finding the minimum, in fact, it's finding the minimum position. So this is the position where the smallest element that we've seen so far is located. So what do we need to do? Well, the minimum element that I haven't seen is 1. So now I'm going to place 1 there. Then what? Well, I have a list of size 1 that's sorted. Everything else is possibly jumbled up. So now what do we need to do? We need to find the next item that we have and find the minimum. Well, that's 2. So in this case, I'm going to swap out the values 2 and 3. Now, I'm just going to do a swap here rather than shuffling everything up, because that shuffling is going to take time. Every time I do that assignment into an array, it's going to take time. Whereas here, I'm just noting the position, and I'm doing a swap. So that's different than when we were doing insertion sort, when we were actually shuffling the items, creating a hole where we could insert the item. Okay, so I swapped 2 and 3, but now I have 1 and 2 that are sorted. Now I need to find the minimum everywhere else. Well, that's 3. So I'm going to swap 3 and 4, and that's what we see here. So now I have 1, 2, 3, and then some other stuff that isn't sorted. So what's the minimum after here? It's 4. So I'm going to swap the 4 and 5, end up with what we have here. So the first 4 elements are sorted. Everything else is jumbled up. So now what? I want to find the minimum that's left here. Well, that's the 5, so I'm going to swap 5 and 9. And so now I have 1, 2, 3, 4, 5 that's sorted. And then other elements. Now I find the smallest over here, that's 6. And then find the smallest that's left here, which is 8. And then finally I have the 1, 2, 3, 4, 5, 6, 7, 8, 9. So just like we had with insertion sort, if I look at this diagonal here, everything below this diagonal is sorted, right? So 1, then 1, 2, then 1, 2, 3, and so on. What we have down here is sorted. So that's how selection sort works. We go through and select the item that's the minimum item that that we haven't seen before, and swap that with the item in the position where it needs to go. Okay, so quizzes 13 and 14. I'm also doing quiz 16 in here. So quiz 16 asked us to sort of walk through what's happening with sequential search and binary search when searching for items in this particular array or this particular list. So let's look at the code for sequential search and binary search. So sequential search is searching on a sorted list that is non-decreasing. So this is what we're assuming. And so I know that after a certain point, I can stop if that element is too big. So, okay, so here's what we want to do. For int I is assigned 0, I is less than 8 at length. That would run all the way through the end of the list if I didn't have anything else. But I want also this condition to be true. The item that I'm searching for is greater than or equal to the ith item. So here, whatever I is between 0 and 8 at length minus 1, I'm going to look at that value and say, well, is k greater than or equal to that? As long as that's true, I mean, if they're equal, then I can just return true. But if k is greater than a sub I, then that's an indication that I still haven't exhausted every possible place where this item k could be located. So I just put in a little print statement here to print out that value and then a space after that. So here's what we see for Quiz14. So when I'm searching for a value of 24 in this array, I've got to search 8. Well, 24 is greater than 0. 24 is greater than 8, greater than 11, greater than 12, greater than 14, 15, 18. Finally, we get here, and 24 is equal to 24. So I make that comparison with 24 and 24 and return true. Now let's actually go through this other one for 9. So what happens when we're looking for 9? Well, I look at 0. Well, 9 is bigger than that. 9 is bigger than 8. But at this point, note, when I compare 9 and 11, I know that that 9 is not equal to 11, but 11 is greater than 9, so I can actually stop at that particular point. So my code doesn't show it here, but we actually make a comparison with 11 as well. So here's that code. So because this condition failed, we didn't actually print out that value. So we could force that and just change that by putting in this entry here, print out whatever that a sub I value was. Well, of course, I is only defined in this loop here, so so we would need to make another variable or declare I outside of this loop to actually have that last entry paired or printed out. So so let's not worry too much about that. But the last one that would be compared is 11, even though it's not printed here. Okay, now what about binary search? So I'm doing binary search for 24, for 9, as well as 25. So note that 24 is found, 9 is not found, and 25 is found. So let's think about what has to happen in binary search. So binary search is a process where we start at the middle, we look at that middle element, and either the item is there, or it's to the left of that, or to the right of that. So I have 3 variables that I'm keeping track of where my search space is. Low, high, and the midpoint. So initially, I start at the beginning of the array 0. The high point is the last element of the array, and the midpoint is halfway in between. So just the average of those two. So now what? While the low is less than or equal to high, here I had actually, I think, a typo or a slight error in the code originally, but this should really be less than or equal to. So when we print out, so I could print out this midpoint value. So note that the first time we tried binary search, I'm printing out 24. And so 24 is what's printed out. And of course, that's the value I'm looking for, so I return true at this point. The next time, we're searching for 9. So let's think about what happens when we're searching for 9. Well, 9 isn't at the midpoint, but 9 is less than m, so we decrement the high, or change the high so that it's the midpoint minus 1, and so on. So let's go back up here and see what happens. So this is my midpoint, 24. So I'm looking for 9. 9 is less than 24, so that means it has to be somewhere over here. Well, where could that be? Well, I want to go to the midpoint. That would be 12. So that's the next value that I compare to here. And 9 is less than 12. That means that it has to be over here somewhere. So I go to the midpoint of this, which is 8. Well, 9 is greater than 8. So that means the only place that 9 could be, if it exists in this array, is right here at this position. That position has a value of 11, so I can return false. Note that the length of this array is 15 elements. So that's 1 less than 2 to the 4th power. So I'm able to actually do this binary search in 2 to the 4th. I'm guaranteed to have an answer in, because 16 is 2 to the 4th, I'm guaranteed to have an answer in less than 4 steps, less than or equal to 4 steps. Okay, in this case of 24, it found it in 1, but in these other two cases, it's going to take 4 trials. So what if I'm searching for 25? What do I do? Start at 24. Well, I say 25 is greater than that, so I'm going to have to go way over here and find the midpoint. The midpoint of this list here is 29. Well, 25 is less than that, so it has to be somewhere here. The midpoint is here, and so 25 is less than that. The midpoint is there, and that's the item that we're looking for. Therefore, it's true, and we're done. So that's sequential search, binary search in a nutshell, plus we did the insertion sort and selection sort. So those were quizzes 14, 15, and quiz 16.